Jnanam paramam dhyayam. Knowledge is supreme.
I am Zai More and I will be doing TAing this quantum mechanics course conducted by Professor Ramadevi. And in the tutorials, after every 4 lectures, as you know, that there will be one tutorial, and these tutorials will consist of 4 to 5 problems based on the lectures which you have seen, which will be posted before the tutorials. And then from tutorials will basically help you to understand more the theoretical part. So I will try to put some important steps while discussing the tutorials, and then there will be some in between step that you can work out and then understand the problems in a better way. So let us get started to the tutorials. This first tutorial consists of 5 problems based on what we have already seen in last 4 lectures, which will basically have more problems on particle in one dimensional box, find out the probability density, expectation value, etc. So as you can see, the first problem is divided into 3 parts. So the first, let me read out the question. A particle in one dimensional box has the following normalized wave function at time t is equal to 0. So time independent wave function is given to you, and you are asked to find out the time dependent wave function. And then the second part of this question is what is the expectation value of the energy at time t is equal to 0 and at another time where t is some capital T. And the third part of the question is what is the probability of finding the particle between the position x is equal to 0 to x is equal to a by 2 at some instant of time. Okay. So let us get started with the problem. So first problem, wave function, time independent wave function is given to us, which is this constant times this is given to us, and in the next step we will try to write this in a simplified way. So I will just open up these brackets. So this would give me pi x by a plus, here I will simplify this cos theta sin theta, that is 2 times cos theta sin theta will give us sin 2 theta. So I will just write it in this form, that will be sin 2 pi x by a. Okay. We can simplify this expression again by writing it into the known form. What is the known form? That is, we know what is the solution of one dimensional for a particle in one dimensional box. So we will write the normalized wave function as this, we all know, we have seen already in the lectures, sin pi x by a. Okay. This is one term. The second term I will rewrite as sin 2 pi x by a. So for this, just recollect what was the solution for a particle in one dimensional box. Psi of x was given by, or rather let us call it as phi of x. Pi of x was given by 2 pi by L sin n pi x by L. This was the general solution where n can take any value. Okay. And the corresponding energy E n was given by n square pi square h cross square upon 2 m L square, where L was the length of the box or the width of the box. In this case we have it as A. So now what do we have? So using this, you can see in the first expression we had this was my phi 1 of x, this is nothing but phi 2 of x. Okay. So here n is equal to 2, here n is equal to 1. So now what I can do is, coming back to this, I can write this wave function as, we have the constant as 4 by 5 phi 1 of x plus we have 1 by 5 phi 2 of x. Now we have to evaluate the time dependent wave function, that is psi of x comma t. So now you can see from this relation, so E1 will just correspond to pi square h cross square upon 2 m L square, and similarly for E2 you can evaluate. So this can be written as 4 by 5, this is my phi 1 of x, and I have to put the time component which is e raised to I E1 t plus the latter part will have phi 2 of x e raised to minus I E2 of t. This is nothing but the time dependent wave function. Okay. This is a simple way. So this is the first part where we have to calculate the time dependent wave function. Okay. So now let us go to the second part of the problem. In the second part of the problem, you are asked to find out the expectation value of energy, that is the energy operator. How do we calculate the expectation value? The standard way of writing this is psi star x comma t e psi of x comma t. This operator E, we can write it as I h cross dou by dou t. This is the representation of the energy operator. Okay. As you know that momentum operator is represented as minus I h cross dou by dou x. Similarly, the energy operator is represented by I h cross dou by dou t. So now what we do is we will solve this. So here you will substitute dou by dou t, and then when you differentiate psi of x comma t with respect to t, the energy component, that is E1 and E2, will come out in the derivative. So finally what you obtain, you will have to write explicitly psi star and psi and operate E on I h cross dou by dou t. Okay. And then what exactly you obtain in the end is 4 by 5 E1 plus 1 by 5 E2. Okay. Now here there are 3 steps involved, and it is very easy to work out. You have to just substitute psi star psi and this operator and work out these steps and just check whether you obtain this equation. Okay, one more remark, we have seen that E n is n square pi square h cross square upon 2 m a square in this case. So what will be E naught? E naught we will write for n is equal to 1, our E naught is equal to E1, which is nothing but, okay, this is pi square h cross square upon 2 m a square, and we can write this E1 and E2 in terms of E naught. Simply I can write this as 4 by 5 E1, I can write it as E naught plus, so here E2 will, E1 is just E naught, E2 will be n square times E naught, which is nothing but 4 by 5 E naught. So in the end what I obtain is this. Okay. So the second part of this problem is, this is the solution. Okay. So this was part B of the problem, And now let us go to the part C. Okay. It is again very simple to obtain part C, which is you have to find out the probability of finding the particle. So, probability, how do we obtain probability in general? Probability of finding the particle is psi star psi dx. This is the shorthand notation. You will write it as x comma t and here also x comma t. So, let me write it again, psi star x comma t psi x comma t dx. Okay. And for the normalized wave function, the probability of finding the particle in a box from 0 to say a length a would be 1. But here we have to calculate the probability from 0 to a by 2. Okay. So, now what do I do is again I substitute for psi star and psi in the expression, and then I will write I will skip one step. So, what you obtain basically is phi 1 square term with a weight factor of 4 by 5 plus dx plus 0 to a by 2. I have a weight factor of 1 by 5 with phi 2 square, okay, and I will have 2 more terms, that is 2 by 5, I forgot here dx, 0 to a by 2. I will have a cross term, that is phi 2 star phi 1, and another term where I have phi 1 star phi 2, okay, and these are all real wave function. And when you perform this integration, you will obtain, phi is a normalized wave function. So, you will simply obtain 4 by 5 and you have integral from 0 to a by 2. So, you will obtain a factor of half. So, adding these two terms you obtain a factor of half, okay. And in the second part you have to work out these integrations, okay. When you write phi 2 and phi 1, the x part, that is the space part, will remain the same, but the time component will have exponent plus or minus E1 minus E2 or E2 minus E1, depending on that you will simplify these expression, and then after performing the integration from 0 to a by 2 you obtain this result. So, in between step I expect that you can work out, it is not that difficult. So, I have a 16 upon 15 pi cos, it is E2 minus E1, which I can write it as 3 pi square h cross square upon 2 m, and you have a square, okay. And I have a t cos theta times t, I mean this E2 minus E1 times t, but we want to find the probability at time t is equal to, we have to find the probability at time t is equal to capital T. So, I will put a capital T over here. So, the probability expression comes out to be this. For a particle in one dimensional box, you always need to remember that the normalized wave function is given by the expression which I have shown you in before, that is this one and this one. So, the normalized wave function or the solution for a particle in one dimensional box is given by this, and the corresponding energy eigenvalue En is given by this expression. Second problem is also a problem based on one dimensional potential box, but here we have a potential which is non-zero. So, you consider a particle in one dimensional potential V of x, which is infinity for x less than 0 and x 0 and a. So, between 0 and a, the potential is 0. For x greater than A, the potential is V0. So, let us draw this question 2. Let us draw this. So, how will the diagram would look like? If you consider between 0 and A, the potential is 0, and so x is 0, x is A, this is the x axis, and here V is infinity. So, at x less than 0, V is infinity. So, this is your V axis, and for x greater than A, V is equal to V0. So, this is V. So, V will be equal to V0, some V0. Okay. So, you are asked to find out some relation between these energies and the potential, that is, show that the bound state energies are given by a transcendental equation, and you can also, like, if once you achieve this transcendental equation, you can actually visualize what will be the form of the wave function. We will divide this in 3 regions. Okay. So, let me call this as region 1, this is region 2, and this is region 3. Okay. So, we will be using our knowledge of what we have learnt in the lectures. So, this is the region 1. So, in region 1 what do we have? In region 1, okay, what do we have? V of x is 0, okay, for x less than or equal to 0. So, what can you say about the wave function? Wave function will also be 0. Okay. And then so let me label this as psi of 1, region 1. Then in region 2, what can you say about the region 2? So, in region 2, I am sorry, here we have V of x is infinity, because I have already drawn it here, V goes to infinity in region 1. So, in region 1 V of x is infinity for x less than 0, and the wave function is 0 at x is equal to 0, as we know. Okay. So, for a well behaved wave function, we need to satisfy some conditions. So, one of the thing is that the wave function will be 0 for x equal to 0. So, at the boundaries the wave function must vanish. So, now let us come to region 2. So, in region 2 we actually had V of x is 0 and x is between 0 and A. Okay. So, for this region we will write down the time dependent Schrodinger equation, time dependent. So, let us write down the time independent Schrodinger equation, d square psi of x upon dx square is equal to E psi of x. Okay. So, here you can see that V of x is 0. So, I have directly written down this expression. Again let me call this as region 2, okay, and E. So, E has to be greater than 0. Okay. So, E is greater than V, and similarly you can find out the solution for this wave function simply by simple algebra. You can find out that this wave function which I wrote for region 2 can be written as A sin k1x plus B cos k1x. This is the general solution for this equation which we had written down before. K1 is nothing but square root of 2 me upon h cross square. Okay. Now, we can use boundary condition. So, using boundary condition conditions, what we can do is we can write down the correct form of the wave function will be. So, at boundaries, that is at x is equal to 0, what do we obtain? At x is equal to 0, psi of x is 0. So, a sin k1x plus b cos k1x is 0. That would imply simply that b is 0. So, this is what we obtain. So, let me write what will be my psi 2 of x. Psi 2 of x will be a sin k1 x. We have region 1, wave function is 0, region 2, and now let us go to the third region. In region 3, v of x is equal to v0 for x greater than a. Okay. So, what do I have? How will I write this? I will write this as d square psi 3 of x upon dx square plus v0 of x psi 3 of x is equal to e psi 3 of x. Okay. Now, again it is easy to find the solution of this wave function. Psi 3 of x, again what we can do is we can write this as, okay, let me write this as d square psi by dx square. I just rewrite the above equation as, I will rewrite this above equation as 2m, I will just take this here, I have e minus v naught upon h cross square, okay, and this term I will write as psi 3 of x. So, this term I call it as k2. Okay. So, the solution of this is given by psi 2 psi 3 of x is equal to c e raised to I k2 of x, where k2, so this is nothing but k2 square. So, k2 is nothing but 2m e minus v naught upon h cross square. Okay. So, this is the third wave function. Okay. And then now what we do is, again here I have skipped some step, you can apply the boundary condition and get this as the final expression. And in the final step what we will do is we will use the continuity. Condition, continuity of psi of x. Okay. What is that? That is at x is equal to, so we had this psi of x at x is equal to a should be equal to psi of, so from region 2 to region 3 at x is equal to a should be continuous. So, using this what I obtain is, I have sin k1a is equal to, the previous one was c e raised to I k2a, and the continuity at continuity of psi of prime of x will be, I will do the same thing for psi prime of x at x is equal to a should be equal to psi prime of x at x is equal to a. So, this will give me another set of equation, sine will become cosine and I will have minus k2 c e raised to I e raised to k2 a. So, finally, what I obtain in the end is, when I just, you have to divide the two equation, and then what you obtain finally is tan of a k1, okay, and which is equal to, you have minus k1 upon k2, okay, which is nothing but what is given to you in the question. Okay. So, this is the final result. We can again rewrite this k1 to write it in the final step is a 2m e in the square root, because we know what is k1 and k2. So, I am just resubstituting for k1 and k2 is minus e upon v minus v naught minus v inside the square root. And now you can, using this you can easily sketch the form of the wave function, how the wave function would be. Okay, that I leave it to you all. Okay, so this is what we have done for the tutorial 1 part. This was part 1, and the remaining problem we will discuss in the later part.